Okay, so last time we talked a little bit about linear transformations. Now what I want to do this time specifically is focus on linear transformations and what they do to areas. Okay, so for instance, so recall the following features. We said linear transformations being a special case of affine transformations do the following: they map lines to lines. Okay, so this is a, so what all do we know? Linear transformations certainly map lines to lines, well, or points, as we mentioned last time, could map some lines just to a single point. And what else does it do? Well, what does it do to lengths? What does it do to angles? Now answers to these questions at least we know through the various examples that we have looked at before. So there are instances of linear transformations which preserve lengths, and there are others which might uniformly increase length by some factor, and yet others which might do neither of these. They may along some directions increase length by some factor, along a different direction they may increase length by some other factor, and so on. So as far as lengths are concerned, well, there is nothing uniform that you can really say. Okay, so can't say much really about lengths in general if I don't know any extra information about the linear transformation. Similarly, angles, again we looked at instances of transformations which preserve angles such as rotations, reflections, dilations, and so on, but then there were instances, sort of the inhomogeneous dilation for instance, which did not preserve angles. So again we can't really say much. Okay. So a typical linear transformation might deform the plane in such a way that neither lengths nor angles are preserved. Okay. So it does strange things to these guys. Now areas is sort of the third aspect that we studied in our various examples. So what is the typical thing we want to do? Let us do the following. Let us pick some region in the plane. So for instance I could take, so just to make life simpler, let us take a polygonal region, okay, by which I mean let us say I take a region bounded by lines. It need not be a regular polygon or anything like that. So I could take say something like this. So here is a region R that I write down on the plane. I am allowed to choose various possibilities. I could take maybe a triangular region or a square, rectangle, pretty much any sort of polygonal region that you can think of. And what I want to do is to study the effect of applying this function f. So let me say that I have a function f, a linear transformation. So let f be a linear transformation. Okay, we could in fact also allow affine transformations, but let us just stick to linear for now. I want to look at what f does to this region R. Okay. So the first thing is, as we said before, it is sort of enough to really figure out what happens to each of these various vertices. So what f would do is to map these vertices to some points. So there would be, let us say 1, 2, 3, 4, 5. So maybe I have again 5 distinct vertices. So maybe it deforms it in some other fashion, right. So it may not have the same form as the original region. So this is my region R, and maybe that is my region R dash. Okay, and R dash is just the image of R under this map. Okay. So I am just sort of depicting something schematically here. It is probably not a very good picture in general. So now here is the question. I want to compare the area that is enclosed by the region R with the area that is enclosed by the region R dash, right. So this is the typical thing that we had looked at earlier. By what factor does the area increase or decrease? So here is the question. I want area of the region R dash. So R dash is what we would call f of R, that is the image of R under the function f, let us call it R dash, divided by the area of R. This you might want to call the area scaling factor or the area dilation factor. Now here is the surprising fact. if f is a linear transformation, then this ratio is a constant independent of what shape R has or where it is located on the plane. Okay, so surprising fact, if you wish, if f is a linear transformation or in fact also an affine transformation, then this area scaling factor is a constant by constant I mean it does not depend on, it's independent of the region R. It does not matter what shape the region has, where it is located and so on and so forth. So it is absolutely independent of R, the answer will always be the same. Okay. And so what does it mean? In other words, f dilates area uniformly by this constant. Okay. So let us give this constant a name, let us call it say delta, this is a constant. So in other words, i.e. f dilates areas uniformly by this factor. Okay. So all areas expand by the same amount, that is basically what this means. Even though, so why did I call this somewhat surprising? Because lens for instance could suffer different amounts of dilation in different directions and so on, but when you talk about areas what you get is the same uniform dilation. Okay. So let us just do this again by example. Let us take f to be, well I guess I am just taking the most general example, f of xy, I said it is a linear transformation, so it is something which looks like this, right, ax plus by cx plus dy. And let us see what this dilation factor, area dilation factor delta could be. So in order to do this, let us take a simple figure R, let us just take the unit square. So I will take the origin 1 0 0 1 1 1, think of this as being my region R. So R of course has area 1 in this case, it is just a square of side 1, and I want to apply this function f to it. Now observe that applying this function f does the following, it maps this square to, well in general a parallelogram. So here is what the square maps to a parallelogram. Okay. So how do I deduce this? Well, I will just figure out the 4 endpoints. So for instance the origin maps to the origin, I just plug in 0 0, 1 comma 0 maps to the point a comma c by plugging in, this maps to the point BD, and the point 1 comma 1 maps to, well a plus b comma c plus d. So these 4 are in fact vertices of a parallelogram. Okay. And so now the question really is, in order to figure out this dilation factor, so let us just work out, so if for the moment let us accept this fact as being true, that this dilation factor is uniform, there is just a single dilation factor delta. So to figure out what delta is, all we have to do is take this particular choice of R and R dash. So I will compute the area of the parallelogram and divide it by the area of this rectangle. So let us compute this scaling factor delta is just the area of the parallelogram divided by the area of the original region R. Now of course the original region has area 1, so I do not need to do anything there, all I need to figure out is the area of the parallelogram. Okay. So of course the area of the parallelogram, there are several different ways of trying to compute the area of a parallelogram, but here is one. So if you have a parallelogram in general, so let me just say just a brief detour, talk about areas of parallelograms and formulas for those. If I have say here is theta, the angle, now the usual formula says it is base times altitude. So let us maybe call these two sides as something, we will call this P and Q are the two sides. The area of a parallelogram is just base times, so P times the altitude. So area equals length of the base times altitude. So the base is just p, and the altitude, so just by elementary trigonometry, is q sin theta. Okay, so q sin theta is this vertical line segment here, and so it is p times q times sin theta. Now and of course sin theta, so the angle here could be, it depends on what the angle is, something between 0 and 180 degrees. Now what do we know about this quantity here, pq sin theta? We could try and compute it in various ways, but the easiest way to do this is just by using, going back to our definition of vector cross products. So recall, so we have already talked about cross products in one of the earlier lectures. So recall, if A and, so I will just use notation for vectors, if vector A, vector B are two vectors, then their cross product A cross B has the following magnitude. The length of the cross product is exactly the length of A times the length of B times sine of the angle between them. Okay, so I'm actually sort of appealing to some previous knowledge of cross products. So this just makes it much easier. So if you are familiar with this, it is quicker to get to the area formula. If not, there are sort of other ways that you must play around with in order to get to the same answer that I will get to in a moment. So what this says is, to find the area of a parallelogram, you just think of the two sides as being vectors. So you think of this as a vector, this as a vector, and the area is just the magnitude of the cross product. Okay, so that's a very nice description of the area. So let's just apply this to this situation. So let's come back here. We were trying to figure out the area of this parallelogram R prime. So what we want to do is to think of one side and the other side as both being vectors. So this is nothing but the absolute value of the cross product of these two vectors. Okay, and now I will use vector notation again. So recall that I cap and j cap are often the standard notations for the unit vectors along the x direction and the y direction. So I have this vector is a I cap plus c j cap cross product with b I cap plus d j cap. So that is the cross product of these two vectors, and I need to find the magnitude of the cross product at the end of the day. And so here what you need is the definition of the cross product. So if you actually just compute this cross product, here is what you will get. It is going to be, so this is the magnitude of, so for instance I cross I is 0. So you should just think of this as, you need to expand this out completely, distributing it using the distributive law. I cross I is 0, I cross j is k. So this just gives you AD times k, and then the other term there will just give you minus BC times k. Okay, and k cap is just a unit vector along the z axis, and so this final answer here is just the absolute value of AD minus BC. Okay, so what does this mean? Well, this just says that this dilation factor, so here is the conclusion, the dilation area dilation factor delta is nothing but the absolute value of AD minus BC. Okay. And now what are A, B, C and D? Recall, those were just what appeared in the definition of the function. The linear transformation is exactly Ax plus By, Cx plus Dy. So the A, B, C and D are these four numbers, right? And recall again that last time we had said these are best encoded in the form of a 2 cross 2 matrix. So you should really think of this linear transformation as being encoded by this matrix A, B, C, D. And now that we do this, the number AD minus BC again has another interpretation. So AD minus BC, recall, is just what we would call the determinant of this matrix. So recall that the determinant of this 2 cross 2 matrix here is exactly AD minus BC. Okay. So what this means is that the scaling factor has a natural interpretation in terms of the matrix of the linear transformation. So thus conclude that the scaling factor delta is nothing but the absolute value of the determinant of the matrix of the linear transformation. This is the final conclusion. Okay. So in general, for an arbitrary linear transformation, if you are given the transformation f itself and you want to know by what factor does it scale areas, all you want to do is to just write out the matrix corresponding to the linear transformation and then compute its determinant. Okay. And the absolute value of the determinant is exactly the thing that we want, the scaling factor. Okay. So returning in some sense to something we started out with, let us just do the same thing for functions from R to R. Okay. So let us do the following, let us go one dimension lower. Instead of considering functions from R2 to R2, let us consider functions from R1 to R1. So by which we mean just functions from the real line to itself. And here what would a linear transformation mean? Well, a linear transformation from R1 to R1, just copying the definition that we used for two variables, a linear transformation now can only act on one variable and only give you one real answer. So I mean there are no two components. Well, it is just something of the following form, it is just Ax. If I had two variables, I can do Ax plus By, Cx plus dy and so on. If I only have one variable x, all I can do is just multiply it by some constant. Okay. And such a thing is what you would call a linear transformation in one variable. So A here is some constant. Okay. So such a thing is a linear transformation. Now, well, so again you could try and do the same notions that we had earlier. For instance, we can now talk not about area dilations but of length dilations. So you could now ask the following thing, since we are now in just one dimension, the notion of area is most naturally replaced by lengths. So for instance, you can ask, suppose I took a line segment of some length L and I apply the function f to it, what will be the new length of my line segment? Okay. So for instance, let us say imagine the line segment starts at 0 and goes till L, and now we apply this function f to it and ask what happens to this line segment. So let me call this interval, let me call it I is my interval. I apply my function, f of 0 is 0, and of course by definition f of L is just the point AL. Okay. So this interval I, when I apply the function f, just becomes potentially a larger interval. So if A is for instance 2, it is an interval of size 2. Okay. So this is my new interval I dash. And so now you can ask, what is the length dilation factor in this case? Okay. So here the length dilation factor for the map f is the following, it is just the length of I dash divided by the length of I, and observe here that I dash has A times the length of I, right. This is AL and this is A, so this is just going to be A. Okay. So this of course if A is positive, if A turned out to be a negative number, then what you would get would really be the same interval but in the opposite direction. Okay. So the length in that case should really be the modulus of AL. So actually speaking, if A is negative, since both top and bottom are positive numbers, what I should get out as an answer is a positive number. So here is the general answer, the length dilation factor for maps from R1 to R1 is just the absolute value of A, just the absolute value of the constant in front. Okay. Now observe again that just like linear transformations from R2 to R2, here the length dilation is uniform, pretty much no matter where you keep this interval of length L, no matter where you place it on the real line, it will always be expanded by the same ratio A, okay, by the same factor A. So this is what we mean by uniform length dilation, it always expands by the same factor. independent of where it is placed. Similarly, in the case of R2, no matter what the shape of your region and no matter where it is placed, it always expands by that same factor delta, which is the determinant. So now let us just make this a little bit more general. So here is one final point about general functions from not linear transformations. If we just take an arbitrary function from R to R, okay, so let us say it is a nice enough function, say maybe it is a continuous function, it is a differentiable function, things like that. So imagine a nice smooth graph of this function. So if I have say an arbitrary function, sufficiently nice and arbitrary for now, let us ask for the same dilation factor business. So here is what it means. So I have this function f, it is not linear necessarily. What I want to do is the following: I want to take a point x0 on the real line, I want to take an interval, so I want to take say an interval I, one of whose points one of whose endpoints is x0. Okay, so I take x0 and x0 plus say the other endpoint, let us call it delta x. Okay, for now delta x is just any real number, but eventually we will think of it as being a very small real number, so that this is a very small interval. So I pick some interval around x0 or with x0 as one of its endpoints and ask, well, what happens to this interval when I map it under the function f. Okay, so what happens to the two endpoints, for instance, x0 will map to the point f of x0, the right endpoint will map to say this right endpoint x0 plus delta x. Okay, so the new interval I get is exactly this guy here, I dash. So now I can ask for the same question, what is the dilation factor, what is the length dilation? Okay, from comparing I with I dash, well, this is the length of I dash, the length of I dash divided by the length of I, and that is exactly, well, what is the length of I dash? It is f of x0 plus delta x minus f of x0. Well, actually I should put modulus because I do not know f of x0 plus delta x could be to the left of f of x0. In my diagram I have drawn it to the right, but I do not know which way it lies. So it is the absolute value of this difference divided by the length of I. The length of I is exactly delta x. Okay, so this is just, so delta x is anyway positive, so I can just put it within the modulus. So here is the answer, the length dilation factor comparing I with I dash, so this is what we would sometimes call, it is the length dilation factor at the point x0, right. Observe, if I change I to lie somewhere else, then of course the length dilation factor will have to take those two endpoints into account. So the length dilation factor at x0 is really this quotient here, and now I will think of delta x as being a smaller and smaller number. Okay, so we now let delta x also approach 0, let it go to 0. So when you do this, what you are doing really is taking smaller and smaller and smaller intervals around x0 and asking by what factor is their length dilated by this function f. Okay, and so we want to really consider the limit of the right hand side as delta x goes to 0, and that limit is really, well, it should be familiar if you have seen this before, is just the derivative, the limit as delta x goes to 0 of this quotient so this quotient here is of course just the derivative. So assuming the derivative at x0 exists, that this limit exists, what you have is just the absolute value of the derivative at that point. Okay, so what this analysis tells us is the following geometrical interpretation of the derivative. The absolute value of the derivative essentially tells you the dilation factor at that point. Okay, so what is this? This is exactly the dilation, length dilation factor of the function f at the point x naught. Okay. So, all it is doing is just keeping track of the amount by which intervals get scaled when those intervals are in a small neighborhood of x naught. Okay. But observe that unlike the case of a linear transformation, this is not uniform. The derivative, the value of the derivative may not be a constant at all points, right. It is of course a constant if f is a linear transformation. So, observe if f of x is just the function ax, then we said that the length dilation factor. So, if you compute f prime at x naught for any point x naught, the answer is always a. So, the absolute value is just the absolute value of a. Okay. This is independent of x naught, this is for all x naught. That is the reason why if it is a linear transformation, you always get a uniform dilation. The amount of dilation is always modulus of a, no matter what point x naught you are talking about. But for a general function, for a general differentiable function, this may not happen. For different points x naught, the value of the derivative might be different, right. And so, what the function really does is to dilate intervals differently depending on where the point is. So, this is really a non-uniform dilation in general. Okay. But nevertheless, this particular geometrical interpretation is useful to keep in mind, and this is partly why we talked about area dilations. For example, in the case of maps from R2 to R2, the more general thing there. So, the natural question here is, what if we were not considering linear transformations from R2 to R2? What if we had a more general function from R2 to R2, say differentiable and so on? Then it turns out that you can still try and figure out what the area dilation factor would be, and that would now involve the notion of partial derivatives. Okay. So, that is the reason, or that is one natural way of thinking about what partial derivatives do. They really give you a way of trying to compute the area dilation factor at each point. Okay. So, we will talk a little bit more about all this next time.